So this video lecture is intended to cover the material we didn't get to in today's class on surface tension. Now, surface tension is a term you've probably heard before. It's what allows things like this water strider here to sit on top of the water in much the same way that you or I would stand on a trampoline. It's also what allows people to do this neat trick with a razor blade, where even though a razor blade is constructed of steel, it's 8 times the density of water. If placed carefully on top of the surface of water, it'll actually float. Now, if perturbed enough, if shoved through the surface of the water, it'll sink rapidly, just as you'd expect steel to do. So let's explore very quickly what causes this to happen. What are the physics and mechanisms behind surface tension? So for this, I'm going to go ahead and open up a sketching pad. Now let's consider a tank of liquid with a free surface. We use this triangle and a couple of horizontal lines to represent a free surface. So fluid particles that are inside or are immersed inside this fluid tend to experience what are called cohesive forces, repellent or attractant forces. But they repel or attract with their neighbors equally in all directions. That is, because it's surrounded by other fluid molecules, those cohesive forces act from all directions. And the result is a balanced force, or a net zero force on the molecule. So it's not getting pushed or pulled in any one direction. If we take a particle that's on the fluid-free surface now, it's missing half of those neighbors. So what it experiences are an unbalanced set of forces that makes these particles along the fluid surface cling together and experience tension between them, which is why we call this surface tension. Now, we define surface tension, or we denote it with the symbol sigma. And if you're paying attention, you might say, well, that's a problem, because earlier we defined sigma xx, sigma yy, and sigma zz as being normal stress. This is true. And really what it means is you're going to have to be careful. So if you see sigma, look for the subscripts xx, yy, zz. That means we're talking about normal stresses. If there is no subscript, then that means we're talking about surface tension. In the extra handout that I posted on Canvas about surface tension, I believe they use the symbol gamma. That would be an option too, but we're going to use gamma for something else important later in the course. So no gamma for us. We're going to stick with sigma. Remember, no subscripts, no xx, no yy, no zz. We are talking about surface tension. And we say that sigma is equal to the surface tension force divided by some length, which is actually the length over which F sigma acts. We'll call this F sigma. And to demonstrate this more effectively, we'll get to an example in a moment. But before we do that, let's head back to our standby of dimensional analysis. So to figure out the dimensions of sigma, we know that force has dimensions of mass, length, time to the negative 2. And then length, of course, has dimensions of length, which means the sigma has dimensions of mass, time to the negative 2. And you might say, again, if you're paying attention, you might say, well, but earlier we saw that sigma is a force over a length, and mass over time squared seems completely different. And you are correct. But let's, for example, say we're given a value of sigma equals 10 newtons per meter, right? That's a force divided by a length. Now, if we decompose the force here into our mass, length, time system, what we see is that this has dimensions of mass, length, times -2, length. Or if we decompose the units, we may say that this is equal to 10 kilograms meters per second squared over meters, in which case the meters cancels out. We end up with mass times to the -2, and the value stays the same. So let's do an example. Consider a bubble. This bubble is a soap bubble, like one you might blow with a bubble wand in your backyard. Okay, so inside the bubble, there's air at some pressure, Pi. Outside is also air at some pressure, Po. Now, assume first that the pressure inside of the bubble, Pi, is greater than the pressure, Po. And the reason we assume this is because if surface tension is truly tension, then all the molecules of this along the boundary of this bubble are pulling together, much in the same way as a rubber balloon or latex balloon would. And just like a balloon, if you open up the end of the balloon, if you untie that knot, all the air comes rushing out because the pressure inside is higher than the pressure outside. Otherwise, balloons would inflate themselves. Doesn't happen that way. So, the pressure inside of the soap bubble is higher than the pressure outside of the soap bubble. Now, let's take a cut. Let's cut the soap bubble in half and draw a free body diagram of this hemispherical half of the soap bubble. Okay, let's assume that this is the x direction. This has a radius of r. And then because of surface tension, we're going to develop the surface tension forces in the positive x direction, distributed all around this circular cut. At the same time, because as we mentioned, the pressure inside is greater than the pressure outside, we're going to have these pressure-induced forces trying to blow the two halves of the bubble apart. And these are going in all directions. Now, let me move these items. Now, if we project this bubble onto a flat sheet, what we get is just a circle. And the way we compute the force caused by pressures is by integrating the pressure over the surface area of the projected circle. So if this is r, then A is equal to pi r squared. So that means that the net force of the pressure will make this a big, bold line. The net force caused by the pressure difference between inside and outside of the bubble is equal to P. Oops, let me draw this in black. We'll call this FP, right? FP is equal to PI minus PO times pi r squared. Okay. At the same time, we've got all these little intermolecular forces distributed around the ring that connects these two halves of the bubble together. And we're going to call this F sigma. Okay. So if we do a sum of the moments, or sum of the forces in the x direction, then we can write sum Fx equals 0. Why equal to 0? Well, because the bubble's not exploding. we're assuming that the bubble is stable, it's steady, it's sitting there happily, and that the forces are all balancing one another. Otherwise, you don't have a bubble anymore. So we have negative Fp plus F sigma equal to 0. So what this means is that F sigma must balance Fp. So let me go and write it here. So F sigma is equal to Pi minus Po times pi r squared. And before we mentioned that sigma is equal to F sigma divided by the length over which it acts. Now here's an interesting point. The length over which it acts, you might say, is, oh, it's the arc length of this dividing circle. It's 2 pi r. Well, that would actually be wrong. See, because this is a soap bubble, let's look at the edge of the bubble very closely. So let's take a view right here. A soap bubble is actually made up of two free surfaces because you have air out inside, you have air outside, and you have soap inside. Now those intermolecular forces are all developed along each of these boundaries between soap and air. So instead of just one surface, like you have in the case of the tank, you have two surfaces that are just really close together, which means that the surface over, or the length over which F sigma is acting is actually equal to 2 times 2 pi r. That is twice the circumference of the circle connecting the two halves of the bubble. So, knowing this, let's proceed to calculate what sigma is equal to. Sigma then is equal to Pi minus P naught, or O, pi r squared divided by 4 pi r. We can do some cancellations. Squared r pi pi, leaving us with Pi minus Po times r over 4. Now this is a really useful result. It means if somebody gives us a bubble, measures the pressure inside and the pressure outside, and then gives us the size of the bubble, r, we can actually compute the surface tension. At the same time, we can solve for this Pi minus Po term, Pi minus Po, to give us 4 sigma over r. This is also a useful result because it means if somebody gives us a value of sigma, a surface tension constant, and a size of a bubble, we can then compute the pressure difference inside and outside of the bubble. Okay, so there is one problem on your homework dealing with surface tension. It doesn't have anything to do with bubbles. It has to do with what we call contact angles and the meniscus effect. And that information can be found in the assigned reading, and the necessary formula is also contained in the chapter reading. But hopefully, this serves to clear up how surface tension acts and what it causes to happen when dealing with bubbles and different fluids contacting one another.